thanks a lot to Pierre and all the other organizers for organizing this beautiful workshop. Pleasure being here, and it's a pleasure to talk today a bit about bilinear systems, and in particular about some new developments on the simultaneous control of bilinear systems. I have a very, so to say, very tough schedule for the talk, so I will keep the motivation short, because I think you have seen this Bloch equation here now a couple of times. You know this Bloch equation much better than I, and in particular in Dominic's talk 2 days ago is subject to slightly different Bloch equations, but nevertheless you want to control this entire ensemble with one control, and you cannot use the knowledge of the parameter. You take a kind of brute force approach. So the brute force approach would be, let's say, let's compute. So here the control goes to the equator. This is what you want to achieve. And then a brute force approach would be to say, okay, let's compute the optimal control for your nominal system. So the nominal system is the one with the parameter omega 0 and with epsilon equal to 1. And then you can see what happens here. Certainly the nominal system does the right job. If you add some dispersion in the Larmor frequency, all the other systems, they do not end up in the right position. If you have additionally some transverse dispersion, you get this beautiful picture, but you don't want to have it. You do want to have to point all in one direction. And if you add both effects, you end up with this mess. So this is not a good idea to simply compute the control for the nominal system. And then these are these snapshots, what you can achieve if you do this in a more clever way. And I think the math behind these pictures are done by Navin Kanisha and Yeshin Lee. Here in the upper corner, you will see again the evolution. Each arrow here represents one particular Bloch equation for slightly different parameter values. Here in the upper corner, you will see again what the time evolution of all these systems if you apply the nominal control. And here in the lower corner, you will see what you can achieve if you do it in a very clever way. The time scales between the two evolutions are quite different. So what happens is that you will see that in the first snapshot something happens here and then it stays. And then the evolution starts here. This is simply due to the fact that the time scales are quite different. So here you end up again with this mess. Most of the arrows are pointing not in the right direction. And here now the dynamic starts. It looks quite chaotic at the beginning, but finally it's almost magic. All the arrows point in the right direction. And the goal of my talk is that I want to try to explain you the math behind this kind of effect, and to give you at least a sufficient condition under which guarantees that you can achieve something like this. And today last week I talked about, so to say, about the finite case. So the parameter space is finite as in this discretization. But today I would like to focus really on the continuous case. So I really try to control the continuous system. And this is an infinite dimensional one. But first, let's fix some terminology and some notation. A bilinear system for me looks like either this one. This is the equation down, so to say, down on the vector space, and this is the lifted equation on the group level. In the rest of the talk, I will focus on the lifted equation on the group level, because once you know the solution of the lifted equation, you can easily compute the solution of the equation or of the system here down on your vector space. At the beginning, let's assume that your vector space is Rn or Cn, and let's assume that the corresponding operators are simply n by n matrices, either complex or real. Later on, we will pass to the infinite dimensional setting, and there our vector space will be a Banach space or a Hilbert space, and the group will be much more complicated than here. The group of, or the operator space will be let me put it that way. We will restrict to bounded operators. Yeah? They will be still bounded operators, but no longer matrices. They will be bounded operators on some acting on some infinite dimensional space. So probably I would say the most fundamental problem now is, can we characterize the reachable set of the lifted equation? Once we know the reachable set of the lifted equation, we also know the reachable set here of the equation down on the vector space. And the reachable set is certainly nothing else than all states which you can reach simply by varying your controls. And for my purposes, piecewise constant controls are perfectly fine. In this case, you could enlarge your controls even to L1 controls. Yeah? You don't have to restrict to L infinity ones. Yeah?
Sorry for perhaps a silly question, but how do you go back to the vector space from the lifted space? Like, what's the projection?
No, once you know the reachable set, of your lifted equation, then you simply multiply this with x0, the initial value on the vector space, and you get the reachable set down on the vector space. Okay? It's not a projection. Okay, and for simplicity, I will restrict to the case that I have only one or at most two controls. This makes simply the equations a bit simpler. Okay, so for infinite dimensional systems, what should you do? The first thing you should do, you should compute the Lie algebra generated by A. A is usually called the drift term because it cannot be controlled, and B is the control term. So once you have computed the Lie algebra generated by A and B, you compute the real Lie algebra because you have real controls, even if your matrices are maybe in SUN or something like that. Yeah? So once you have computed the Lie algebra, you have this beautiful result which goes back to Brockett, Sussman, and Turchevich, and it tells you the following two things. Let's start here with a subgroup of GLN. Let's assume that it's path connected. If it's not path connected, you can never hope that your system is controllable because your reachable set is path connected. And so you will always stay in the path connected component of the identity. So let's assume from the very beginning that your Lie group is path connected, and to this path connected Lie group there corresponds a unique Lie subalgebra. Let's assume that A and B are in this Lie subalgebra, and then you have the following equivalence. Once you know that A and B do the generated Lie algebra of A and B, so the system Lie algebra of your system, if this is the entire Lie algebra, then you know your system on the group level, it's accessible. Accessible is not that impressive. It simply tells you that the reachable set has interior points. And usually we want to have much more. This is far away from being controllable. But then, you know, if your group is compact, or if your drift term does generate a periodic one-parameter semigroup, then you know that this Lie algebra rank condition here, this one is called Lie algebra rank condition, then you know that this Lie algebra rank condition is even equivalent to controllability. And this is a beautiful result, and this is usually how you approach problems, in particular in quantum control. If you're working with SUN matrices, you compute, you know the group is compact, so all you have to do, you have to compute the Lie algebra generated by your drift term and the controls, and if the Lie algebra rank condition here is satisfied, so if you end up with the entire Lie subalgebra SUN, you know that the system on the group level is controllable. So maybe in your language, operator controllable. Okay, now let's pass to the ensembles. So let's pass to the parameter-dependent systems. Here, this was for one particular system, so let's say for one fixed parameter value. Now let's pass to the parameter-dependent case. So capital P is the parameter set, small p denotes one possible parameter, and I do use this kind of notation usually if the parameter set is finite or countable, so I put the parameter here in the index. If the parameter set is a continuous set like the unit interval, I prefer to use this type of notation. Again, what is important is the control here is again independent of the parameter. So we cannot use the parameter for controlling the system. These systems are called ensembles. This is slightly misleading because it's not really an ensemble in the quantum mechanical sense, but this type of terminology established. So, as I pointed out, important is that the control is still independent of the parameter. And then you are faced, I would say, with two fundamental problems. Let's first look at the second one here. The second one says the same as the other fundamental problem. It says you are certainly, again, interested in the reachable set. And if you assume that the individual subsystems here are controllable, you are interested in conditions which guarantee that the entire ensemble is controllable. This is one problem. But there's another problem here which you have to solve first, and you don't have to solve it, you simply define it in some way. You have to choose the right state space for your system. If the parameter space is finite, so you have 5 copies of your system, you will naturally choose the direct product of your state spaces, no matter whether you have 5 or any other finite number. But if you have infinite, if your parameter space is infinite, you have a lot of different choices. First, think of the parameter space, if you have as a parameter space the natural numbers. Then you certainly can think of different constructions concerning, so you can consider all possible sequences in your state space. You can restrict to certain type of sequences which have some convergence properties, let's say some L2 or LP sequences or something like that. So you can play there a lot. And that is what you have to, so to say, to solve first, or what you have at least, you do not solve this problem, you just simply define the state space you are interested in. And usually the state space, yeah.
So quick question, what is the physical motivation for not considering a finite P? Because for the spins you showed in the beginning, I mean, P is finite, right?
No, in the example, in the beginning, P wasn't finite. It was a continuous set. It was a rectangle. Here, P was the product of these two compact intervals. The discretization later on, the pictures you have seen, there it's a finite problem. But the original problem is infinite. Okay. So, no. Okay, so I will skip that part. Maybe you have enough time at the end, so I will say a bit about the finite case. In the finite case, much more is known than in the infinite dimensional case. But the infinite dimensional case is new for most of the people here, so I will focus on the continuous case. Okay, so this is the continuous case now. So we do assume that the matrices A and B, that they do depend continuously on your parameter. We do assume that the parameter ranges in some compact interval. Then we have these two infinite dimensional systems. Again, the one which evolves on some vector space, as we will see, and here the other one which is, so to say, the group lift, the abstract group lift. For the state space, so for the vector space here, one can certainly choose the set of all continuous functions, because A is continuous in the parameter P. So if you multiply, if you consider this multiplication operator A of P with a continuous function, it's again a continuous function. All you have to satisfy is that your multiplication operators, that the corresponding infinite dimensional space is invariant under these multiplication operators. So you can choose the the set of continuous functions. You can also choose L2 functions or any other LP function. All of these spaces are left invariant under these multiplication operators. So there is a certain degree of freedom of choosing the right state space. For the lifted equation, I would say there is a natural one to choose. And the natural one is the Lie group, the infinite dimensional Lie group of all continuous maps from AB with values in your general linear group. And this infinite dimensional Lie group, or to this infinite dimensional Lie group, there corresponds an infinite dimensional Lie subalgebra, Lie algebra, which is given by all continuous maps with values in the corresponding Lie algebra. So certainly, if the individual matrices here, if all of the matrices belong to SUN, you would certainly restrict this construction here to the group SUN and here to the Lie algebra SUN. So you can certainly restrict these constructions to subalgebras. Okay, and then once we have fixed the state space, we have more or less also fixed the controllability notion, because this state space here, to end up here with the infinite dimensional Lie group, you have to choose a certain topology. It's given by a norm in this case, yeah? And then once you have fixed the topology or the norm, you have fixed, so to say, the controllability notion, and we say that the system is, this ensemble is uniformly ensemble controllable. Usually, since you are working with infinite dimensional systems, you focus on approximate controllability, because you know most of the infinite dimensional systems are not exactly controllable. This is the same, this is also the case for these systems. So you call a system uniformly ensemble controllable. Sometimes you emphasize that you're talking about approximate uniformly ensemble controllability. Whenever you can find, so given a final state, given an epsilon, you can find a capital T and a control here on this interval from 0 to capital P, which steers the initial state, which is in the lifted case always the identity, epsilon close to your final state. And the norm here is the infinity norm, the maximum norm, because you're working with continuous functions and you want to guarantee that the space is complete under this norm. Okay, so what is known about these systems? And there is not that much known about such systems. There's a bit more known for linear systems of this type, but for the bilinear case, I know only a few results, and this one is the one I was talking about before by Navin Khanisha and Yershin Lee, and they proved that for this ensemble here, for this, the parameter is epsilon, and epsilon is varying in this compact interval here. The group they are looking at is the group of continuous functions with values in SO3. They have two control terms, these standard generators of rotations around the x and the y-axis, and then they could show that this system here is approximately uniform ensemble controllable. This was, they published several papers on this topic, and I suggest to look in this IEEE publication. It's more or less a summary, a survey of all the different results they obtained. They obtained also slightly different results with only one control, and here the controls are unbounded. They have also a result for bounded controls, which is much more tricky, and so on. And there's another result by Pierre, Michel Courant, and Karine Bouchard. They proved also kind of ensemble controllability, but here in this work I think it's only a local result, and it's not with respect to uniform, it's with respect to L2, I think so, as far as I remember. And there's a pretty new paper by Agrachev and his co-authors. He invested general control-affine systems, so these systems are much more general than the bilinear ones, but they restrict to controlling constant functions to constant functions. Okay, this is my conjecture. I'll be honest, I cannot prove this conjecture. I can prove a slightly different result, but this is what actually I would hope to be true. So you have here a system involving an SUN. This is your group, so the continuous curves in SUN. You do assume that your drift, that your control Hamiltonian is strongly regular in some sense. This is the condition here. So you have to have the differences between the eigenvalues. They have to be different for different index pairs and for different parameter values. It's a very strong assumption. And you have to assume that the drift term here, that none of the off-diagonal entries vanishes. And then I would say one could hope to have, in the best case, uniform ensemble controllability, or at least, let's say, uniform ensemble accessibility. And I try to prove not exactly this conjecture, but a slightly weaker one during the next 20 minutes. How much? How much? Okay. Sorry. Okay, so let me first sketch the idea. This is my toy example. And this is the one I'm interested in. This is the one we had on the slide 4, so x dot of x of t and p is something like I h0 of p plus I h1 of p x of t and p. This is the one we are interested in, and here comes the toy example. It's the following one. It's an example in SU3 with no parameters. It's simply x dot of t is equal to 0, minus 1, minus 1, minus 1, 0. Let's put plus 1 and here minus 1 plus u of t. There's the control missing. Here's the control missing. And here we have a control of this form, I, 2i, 4i, and all zeros here. Okay. X of t. Okay. Now we know what we have to do. Let's call this one here A. And this one here, B. We know what we have to do. We have to compute the Lie algebra. And we have to check whether the Lie algebra is small SU3. And then we are done in this case. But computing Lie algebras is not that much fun. And you can do it in a stupid way, and you can do it in a clever way. And how should you do this in this example? So first let me define the following notation. Let me define this AT operator. AT B is an operator on, this is small SU3 to SU3, and it maps A is mapped to at B A, which is nothing else than the commutator of B and A. So what you should do, you should consider the B here, and you should consider the following subspace. you apply this add operator to A, many times. You can, certainly there is this I forgot the name. Anyway, you don't have to go through all the natural number. There's an upper limit you have to check. It's about 8 or 9. Okay, so you consider the span of this set. Certainly, this is contained in the Lie algebra, in the generated Lie algebra you are interested in. And it's easy to see it's contained in this set, D0, which is the set of all SU3 matrices of this form, zeros on the diagonal, and something outside. SU3. Okay, but now what you see is this here is an at B invariant subspace by construction, and it's easy to check that it's not only contained in here, that it's all of D0. So, and why is it all of D0? Because A is a cyclic vector for at B in this case. A is a cyclic vector. Cyclic vector of at B, not of at B considered as acting on the entire Lie algebra. It's only a cyclic vector of at B restricted to D0. But this is enough to get all. And you see this, that it is cyclic, that A is a cyclic vector, because you can compute the eigen, or you know the eigenvalues of this operator. You know it's easy to check the eigenvectors of this operator, and you see all of the eigenvalues are different due to the assumption here. You have to check that the eigenvalues are given by the differences here of the diagonal elements. All of them are different, and you immediately see that this guy has a component in each eigenspace, and that is simply linear algebra, which tells you that you end up with everything. Okay, so once we have and then you continue. Sorry, you continue, and you can compute. Now you can compute commutators in this set, and you will see that finally you end up. Finally, you get your entire Lie algebra. Yeah, once you have. So once you have this set in your Lie algebra, then you know that you have the entire Lie algebra. So we can conclude the Lie algebra spanned by A and B is equal to SU3, and then we are done according to Djurjevic, Sussman, and so on. It's controllable. The group is compact, it's controllable. Fine. So now the whole idea of what I want to present you in the remaining part is that the conditions I have written down here, these conditions here, they do guarantee that this guy is again a cycle, the add operator with respect to H1. This is what we have to check. You got the idea, roughly? I hope so. Okay. Cayley-Hamilton was it? It was Cayley-Hamilton. That's the reason why you can stop at k equal to a. Okay. Yeah. So, okay, and to convince you that this is really a cyclic vector of at I h1, it's easier to make a small detour to linear systems, because the same techniques are used in the linear case to prove approximate controllability. And once we have understood the linear case, I think you will believe that it works in the bilinear case too. Okay, so now this is a linear ensemble. It's no longer bilinear because here the term here, the control term, enters linearly. Again, we do assume that A and B are continuous. We choose as a state space here the space of all continuous functions. And I have to make this remark which says that if you certainly you can change the state space here too, you can also consider some LP space, but the results, they will change substantially. So the results will depend on your state space heavily. So then you have again this notion of, or this control problem, this notion of approximate controllability. So you want to find again a control which drives the initial state arbitrarily close to your final state. So what is known about these systems? First, let me introduce the following notation. So to show you that we are really faced with an infinite dimensional system. So we do define this A operator here as the multiplication operator, yeah, with the matrix AP, so x of p times A of p. This is a multiplication operator in your state space. It's a bounded operator, and for the B operator, we can define this here to see that the entire system can be written in this abstract linear form where A and B are now infinite dimensional operators. And we have two first observations. The first says that many standard results in the literature do not apply to this system due to the fact that these multiplication operators, they have continuous spectrum. This is easily seen. Think about the simplest multiplication operator, so to say it's a 1-by-1 matrix, it's just a multiplication by a function. And then you immediately see that the spectrum of this multiplication operator is given by the range of the function. And the range of a continuous function is usually a continuous set. And therefore, you have a continuous spectrum. And what is also easily to check with standard results, you can never hope, even in this case, you can never hope to get exact controllability due to the fact that this operator here or the corresponding reachable map here is a compact operator, and once you have a compact operator, you know there's no chance to obtain exact controllability. You can only hope for approximate controllability. But everything else can be approached more or less as in the finite dimensional case. So you can easily show that this is the reachability map. Using this reachability map and the standard type of Hahn-Banach argument, you can easily show that you have approximate controllability if and only if this condition here holds. And this is simply a Kalman rank condition. Yeah, this is a generalization for the infinite dimensional setting of the Kalman matrix. And the Kalman matrix has to have full rank, and this is nothing else. And then if the system is a single input, so this means that your B operator has only one column, and I denote the single column of the B operator as small b, then you can reinterpret this condition as this one here, which says, consider all polynomials, all real polynomials, plug in this real polynomial, your operator A, multiply the result with B, and consider the spanner. And if this span is again the entire space, you have controllability, approximate controllability. This is simply rewriting this condition in this polynomial language. Maybe Paul Fuhrmann is responsible for that. He likes to express things in polynomial terms. But this now says that B, and now we are coming back to this problem here, this condition here says now B has to be a cyclic vector of A. Okay, and if you understand, in this case, what are the right conditions, I think we have also solved our bilinear problem. And Uwe Helmke and a colleague of mine, Michael Schönlein, they came up with these two beautiful results. The first one gives you necessary conditions under the assumption that you have a single input system, which gives you, the first one gives you necessary conditions which have to be satisfied to guarantee this uniform ensemble controllability. The first condition simply says each individual subsystem, so for each P, the pair AB has to be controllable. This is a quite natural assumption. And the second condition says that consider the spectrum of A to some parameter value and the spectrum of the matrix A to some other parameter value, and they have to be, their intersection has to be empty. And if you add one more condition to these necessary ones, you get a sufficient condition for controllability. And the one you have to add is you have to assume additionally that the eigenvalues of AP are simple. For each P, the eigenvalues of AP have to be simple. And then this gives you the uniform controllability of your linear system, and I can sketch the proof very. It's easy to understand the proof, I think. First, let us restrict to the case that we have 2 by 2 matrices. Yeah? Same arguments apply if we have n by n matrices. Then, this is a heavy restriction. I will comment on this later. First, let's assume that all eigenvalues of these real matrices, let's say that all the eigenvalues are real. Then, due to assumption n1 and s1, you can check maybe by Cato or some other reference that you can simultaneously diagonalize your system with a continuous transformation. And you can also achieve this normalization. Usually, if you choose any of the possible transformations, you would not end up with this normalization. You would end up with a vector of this form, B tilde of P1 and B tilde of B tilde 1 of P and B tilde 2 of T. But then remember that you require that the individual subsystems are controllable. This guarantees that none of these two functions can vanish at some point P. So they are always different from 0, and then you can do some rescaling and you get this normalization. So all you have to guarantee is that these two functions do not vanish, but they cannot vanish due to the assumption n1. So now what we have to do is, we have to speed up. Now we have to compute the span of this transformed system, and we have to check that this span gives you the entire state space. So now consider a linear combination within this space. A linear combination in this space looks like this, so you can write it like this. Now define the polynomial Q in that way, and you see that you can rewrite this condition here as this condition, where you additionally performed this substitution, and you call θ1 is defined by λ1. This is your eigenvalue curve at P, and θ2 is defined by the other eigenvalue curve, yeah, λ2. So this here, with these two definitions, gives you this one. And now you have here and you have to approximate your final state. Your final state is given in terms of the parameter p. But your assumptions on the eigenvalue curves, the assumptions on these eigenvalue curves allow you to invert these two maps, lambda 1 and lambda 2. And you get, and the inverse certainly is again continuous. So now this combination here and this combination, you get again a continuous function in theta 1 and theta 2. And now you have to solve this approximation problem. Here you have a polynomial in theta 1, and here you have a continuous function in theta 1. This reminds you of Weierstrass. Weierstrass is the right one to choose. Weierstrass guarantees you that on a compact set you can approximate each continuous function arbitrarily close by a polynomial. But you have to solve both of these equations. And the trick is this is your parameter space AB. This is the first eigenvalue curve with this range. So this is lambda 1. And there's the second one. And the conditions in the theorem are in such a way that these two ranges here, this one and this one, do not intersect. And that's the reason why you can solve the problem on the union of these two non-intersecting sets. And then you're done. Okay, then apply Weierstrass and you are more or less done. One comment on this is, if the eigenvalue curves are purely imaginary, you can play more or less the same game. But if the eigenvalue curves are really curves in the complex plane, the approximation problem gets much harder. And it was quite hard to find a result. And people working in function theory, they know this result, but we did not. We had to search for quite a while about this approximation result by Mergelian, which still guarantees that you can do this. You have to use a polynomial only in C, not in C and C bar. C and C bar would be trivial. Then you could apply again Weierstrass. Okay, now the theorem which I can prove. This is not the conjecture, this is a V-conversion, because as you immediately realize, I have two controls now. I have two controls, and I have this assumption here again on this strong regularity between H1 and H2. So how can I prove the result now? First, I have to show with the same techniques as here that this guy here is a cyclic vector of this odd operator. And the conditions are precisely such that this works with the same techniques, with the same arguments as in the linear case. But you have to be careful. Certainly, this is not a cyclic vector on the entire space. You have, again, as in this toy example, you have to, again, you have to restrict to matrices which vanish on the diagonal. But in this space, where you consider only matrices or matrix functions which vanish on the diagonal, you can show with the previous techniques that this is a cyclic vector. Then again, as here, you reconstruct the diagonal elements by taking further commutators in the set you already generated. Okay, this shows you that the system Lie algebra is that the system Lie algebra, or the closure of the system Lie algebra, is all of this Lie algebra you are interested in. Then, since you have two controls, you have to remember that if I have two controls, I can really use the commutators to steer the system. If I have only one control, this is delicate. But if I have two controls, I can use really the generated commutators to steer the system. So I have all directions, or approximately all directions, to steer the system. Then finally, I've taken into account that the exponential map here, these are Banach-Lie groups. They behave as in the finite dimensional case. So the exponential map is really a local diffeomorphism. So I can generate a neighborhood of the identity in the group with the exponential map. And then I'm more or less done. That's the proof. And only two final remarks. We did not use any compactness or recurrence arguments. They are delicate, certainly in this case, because the group is no longer compact. It's an infinite dimensional one. And also recurrence arguments are very delicate. Usually the operators you are looking at, they do not generate periodic or quasi-periodic one-parameter semigroups. And one comment about the conjecture I had. Certainly, due to the loss of compactness, one could not expect that one gets uniform controllability, uniform ensemble controllability, but due to the fact that one can easily show that one can generate with the same techniques the entire Lie algebra, one would hope to get at least accessibility, so ensemble accessibility or uniform ensemble accessibility. But even this is not clear because the Lie algebra rank condition breaks down for infinite dimensional systems. There are examples which do generate the Lie algebra rank condition, but which are not accessible. And that's my final remark. Thanks for your attention.